Okay, let's start. I think everyone is done with Tirthankar, and let's start with the calibration, okay? So as I mentioned that we are going to do this two steps. One is bandpass calibration and then gain calibration. But before that, we need to do a delay calibration, which is basically each antenna has a delay or a phase variation as a function of frequency. We are basically trying to correct that using delay calibration, which is mentioned on your document also. So this is the first thing which we are going to do, which is basically a simple delay calibration. So you need a reference antenna. You are basically saying that based on this reference antenna, I will correct for my phase difference of all other antenna. Okay, so my reference antenna delay would be 0, and all other reference antenna, all other antenna with respect to your reference antenna, you find out what is your corresponding delay. That will basically correct you the phase factor, which is something like this. Okay.
So for reference antenna, you can choose any antenna that's working in principle the full time. Like it has all the scans properly and it's not inactive or anything. But prefer to use something within the central square. Usually like C0 to C05 around, because that will like give you slightly better like reliable solutions than like using something like at the end of the arm or something.
Yeah. So I think Atharva and Abhinav already found that C02 is a good antenna. So we are going to use this antenna. So C02, and you find all the other antenna with respect to C02, what is the difference, phase difference. So the task is basically default gain cal. So you first mention the visibility file, which is what the visibility file you are working with. And then you need to mention a cal table. So cal table is when you do a calibration, the solution of that calibration will be stored in your calibration table. Okay, so cal table, and they provide a particular name here, which is this one. So you can provide whatever you want, but it is better to have at least .k1 as it is, just because you can then keep track what is the table you have generated. So if you calibrate, like running this calibration task, all your solution will be stored in your this particular table, which is the name of that is mentioned like this. Okay, so you can also provide this one just to be consistent with everyone. Okay. So I am just basically copy this one and mention it. Okay, and the next task is basically you have to mention the field name. So you are basically calibrating against a model which is 3C147, as you've done it, like you did the Tirthankar's task. You generate a model and which is stored in your data file. So and I am calibrating against that particular model or particular field, which is 3C147. I am also mentioning it here, which is 3C147, and that is the calibration table, right? Then you need to mention the solution interval, which is solint, which according to the document is 120 seconds. So you are basically generating a solution every 2 minutes. Okay. So this phase solution would be as a function of time, and you are generating a solution every 2 minutes. And then you need to mention another one, which is basically reference antenna. So reference antenna is C02. And we already know that this is a very good antenna, like they already found it, so you don't need to do it. But just to remember that in your data, if you mention an antenna which is faulty, your solution would be bad. So there is no meaning to use that antenna. And then you need to mention the gain type, which is K. K is basically corresponding to delay. So that's why you also mention K1 in our calibration table, just to keep track of our own, right? So gain type is basically K. And then you have this one, which is basically solution norm, whether are you want to normalize your gain solution or not. We are keeping it true so that your solution would be normalized by like close to 1, basically. So if you provide all those things, you now do INP, it will come like this. So you have the measurement set, which is your visibility. You provided a calibration table name. This is up to you, but keep it similar so that you can keep track of all these things, right? Then you are basically calibrating against your flux calibrator, which is 3C147. You mentioned that in the field. Then you are generating a solution every 2 minutes. You can reduce that, you can increase that, but it depends on the data. Like you should have enough signal to noise ratio given these 2-minute chunks. So if your data is very good, you can just probably reduce that also. That is up to you. But for this data, 120 seconds is giving you good solution. Then you use a reference antenna C02, you provide a normalized solution, which is solve norm true. And your gain type is K. K is basically corresponding to delay. So you're going to calibrate a delay. So I hope everyone is now at this stage. And if yes, then you need to run go. Yeah, I know you are already there, right? I need to wait for other people. K is basically corresponding to delay. So G is complex gain and K is the delay component of your. So you have e to the power I something, that is the delay, and that delay correspond, like when you do a delay calibration, delay is basically known in CASA as a K, capital K. You have also that G, T, all other thing, right? So K cross is basically your polarization calibration, complex stuff. So we are going to do G and K. G is for the complex gain, which is G, and K is basically delay, or basically you are solving for a phase gradient with respect to your reference antenna. So right now you have a reference antenna. Right now all the phases are scrambled. You are basically start with a reference antenna and saying that from that reference antenna, what is my phase gradient of all other antennas. And you are just calibrating that, storing that solution in your gain table. That's all you are doing. Flux calibrator, you are calibrating everything based on flux calibrator, right? You have a model based on flux calibrator, right? So you know that the flux calibrator, what is the flux of that source and what is the location of that source. So no, if you given that known location and flux, you then solving for phase. Or phase, or here it is your I that term, which is basically called delay, and that is yours. So I hope everyone is at this stage and you can then run go. So it's done. So if you are already able to run it, then you can do LSAR and you can clearly see that there is a new table generated in your path where you are working on. So you mentioned that gain table name, right? And you should have a new table or new this one in your path where you are working on. You can just do an LS in your terminal. So one can ideally plot all these calibration table, but we do not have so much time to plot it. But I am showing you for your purpose, but you can do it later on. Okay. So the gain table can also be plotted in the plot MS task. So you have one task which can plot both the visibility, also the table file. Okay. So I can do default plot MS, INP, and in the Vs, now I am providing the table I have generated. So in the Vs, I am providing the table. So I am providing this one, and since this is delay and this is an antenna based solution, you notice that all these things are antenna based, not baseline based. So I is an antenna, J is also another antenna, right? So you plot it as a function of antenna. Okay. So x axis is antenna, and since you you solve for a delay, so you are providing in the y axis the delay. Okay. So what is the delay corresponding to your reference antenna? So if I do INP, it will show you x-axis antenna, y-axis delay, and I am just providing the calibration table which I have generated. If you do go now, it will show you. Oh, antenna is not supported. Okay, so it should be antenna 1, sorry. In the x-axis, you mention antenna 1, y-axis is delay. So it's basically, you have 30 antenna, and for 30 antenna, what are the delays that is being plotted? And delay is in the nanosecond. So you have very tiny delay amount corresponding to your reference antenna. Only one antenna, which is here, which is number 30, the last antenna, it has large delay, but that may be faulty antenna or something. So you can still keep it, it will not be an issue. You are correcting for that delay component given the largest antenna. Yeah. So you don't need to plot it, I'm just showing you. So you can plot the delay right, with respect to reference antenna, what is the delay of all other antennas, and that is what we are plotting here. Okay. And this is very tiny, it is in the nanosecond. You just like the y-axis in nanosecond. Okay. So after doing this delay calibration, I hope everyone generated this calibration table. Is there anyone who have not done this calibration or? There is.
Is there anybody who has not caught up to this point? No? Okay, so we can proceed.
Okay, so before band pass, Nirupam said that, right? It is actually a function of frequency, but it can also have a time dependence. So we do a preliminary gain calibration as a function of time, provide that calibration table while solving for band pass. So that is what we are doing. So we are breaking this task into two steps. One is a preliminary calibration as a function of time, provide that calibration solution in the in the bandpass calibration. So I'll just show you how to do it. So it is also mentioned here, right? The preliminary gain calibration and initial gain calibration will be done like this. So again, do default gain cal. You provide your visibility file. And then you mention also a cal table. So I am using the same name of the table which is mentioned in the document just to be consistent so that everyone has the same thing. You can just copy this thing here and then you also mention the field name. Okay. And then you are solving for integration time. Okay. So you are solving for G as a function of time. So you are actually providing integration time in a solution interval, which is at the top. It is basically saying that every integration time you generate a gain solution and store it in the calibration table. So this is what you are actually solving for. And then you also need to mention the reference antenna. And then there is a term called minimum SNR, which is 2.0. So if you have a very good data, you can say that minimum SNR is 5. So it's basically saying that in your data, if your signal to noise ratio is 5, you solve it, or otherwise you throw it. So here we are providing 2.0, which is what we found works best. So you have this visibility file here. You provide your gain calibration table name here. You are solving for, again, the flux calibrator. You are solving for integration time. So every integration time you are generating a gain as a function of time. You provide a reference antenna C02, and you also provide a minimum SNR, which is 2.0, which is written that reject solution below this SNR. Okay. So if you have a very good data, you may increase that to 5 sigma. But here we don't have that good data. So typically for VLA, people use 5 sigma or something. GMRT, sometimes 2 or 3 sigma is fine. So we are providing 2 sigma, and now gain type is G, because as I mentioned, I am right now breaking this up into 2 terms. One is solving gain as a function of time, and then I will do the band pass. Okay. So since solution of gain as a function of time is capital G, so that is what mentioned here. So gain type is basically G. Okay. And then cal mode is AP, A for amplitude, P for phase. So you know that gain is a complex quantity. You have an amplitude, you also have a phase. And last thing to mention is the gain table. You already generated a delay. So that table I will mention here. So what it will does is, when they solve for the gain, they will also take the input which is coming from the gain table. The solution we already stored in the gain table. Since we are not applying that gain solution to the data, it will do the on the fly. So you have the gain solution as a function of time, which is the date delay, and that solution will be used on the fly while solving for the gain as a function of time. So as I mentioned, it is also mentioned here, gain calibration tables to apply on the fly. So you are basically solving for one gain, which is complex gain as a function of time, but you also solve for the delay, which is stored in the delay table, and you are providing a table and saying that when you solve for the gain as a function of time, you also take care of the delay component, which is providing by this gain table. That is all it is doing. So I hope you are all at this stage. Okay, I will probably wait for a few minutes so that everyone can finish up to this point, and then we can run. Yeah, you don't need to normalize the gain solution, right? Like, we want to find out what is the true gain. If I normalize by it to 1, that is not desired for the complex gain G as a function of time. Yeah, the previous one, it is required, because that is, you are compensating for the delay, the phase difference. But this gain is overall amplitude, right? You have, so you will have something like this. You have time, you have G. So if you normalized by 1, if your solution is 1, that is basically not right, because your gain can vary. So this G can vary, right? Some anything. We are basically correcting for this G and divide your visibility in the later stage. So this can be like this. Whatever your instrument gain, that should be captured in the gain solution. But if you are normalized, then everything should be close to 1. That is not we want. So if this is 1, you are not actually calibrating the true gain of your instrument. For the delay, that is the phase difference, right? Phase difference is fine. So typically in the complex gain solution, people don't do the normalized equals to true. Then everything would be just 1, like you're setting these two normalized to 1. I hope everything is fine. Sol norm is false. Reference antenna is C02, minimum SNR 2.0. You providing the calibration table here. So let's run this gain. You just do go. So given the minimum SNR, it will basically unable to solve for some range of time. Okay. And you can clearly see here also, there are 100 gain solution as a function of time. Out of that, they tried for 96 and they get 96 solution. Because you provided minimum SNR 2.0, right? So they are unable to solve for 4 samples here. So the next step is basically bandpass calibration. So I will just wait. If everyone has the preliminary gain calibration, then I will go to bandpass. So if you check this IMP, you provide minimum SNR is 2.0, right? So the calibration is basically a chi-square minimization, right? You have this chi-square, you have this sum, you have this measured data ij, you have minus gi gj star. So this is your chi-square, right? And you are basically saying that given you also have noise, your data has some noise. You are basically saying that when your signal to noise ratio, which is your model and over the noise, is 2 sigma, then you basically you take all the solution above that. And if your signal to noise ratio for a particular time chunk is less than that, you will be unable to solve that, just because you do not have that capability to minimize the chi-square. So this minimum SNR is 2. For very good data, you can provide it 5, 6. Like typically VLA C-band data, people will provide 5. So VLA C-band data, L-band data is typically good. For GMRT, it's not that. So it is also mentioned that reject solution below this SNR. So if you are basically saying that you are unable to solve less than 2 sigma. So if you know the chi-square minimization, this is all it is doing. It's not nothing else. So you already have this model from 3C147, Parley-Butler model. You have the measured data. You are solving for GI, GJ, and your data also has some noise. So all you are doing is solving this equation, basically minimizing chi-square to get this parameter. Right? It's a simple linear algebra. It's not nothing complicated here. Okay, should I move to, yeah, go ahead. Yeah. That will depends on for a given time chunk how many samples you have, right? The noise, we have not covered the noise, right? Narendra? Yeah, it's basically is sigma is proportional to some system temperature divided by root over number of samples, frequency, number of time samples, and number of baselines, right? So, but it is antenna based, so you have one, and how many samples you have as a function of frequency and time. This is basically basic radiometer equation, which Saurabh also showed yesterday.
So GainCal people have done GainCal.
So
if the GainCal is not working, then we will not see anything. Probably won't have lunch also. GainCal is done, right?
yeah. Should we go to the plot? Yeah, because all these gain tables will be saved in your folder. You can later on look into that because we are running out of time. So which one? No, that will be in the end, right? Now phase can be within plus minus 180 degrees. This phase will come later on, like within plus minus some 10 degree. This is a preliminary calibration to get the band pass. After that, we will do the final calibration. Could be. Yeah, but it is basically তোমার 100 খানা সলিউশন হবে given the time. তোমার কাছে 96 খানা available point আছে, 96 খানা you are succeeded. So expected attended succeeded. So it's mentioned here, right? Expected attended succeeded. Oh, you flagged, okay.
Channel 0 is always saturated.
Okay.
Okay, can we move
To band pass.
to band pass calibration? Gain calibration people, everybody has done, right? Yeah. Samit, done? It's done, right?
Yeah, so now we are working, we are
Okay.
going to do this BI, BJ terms, okay? And we will provide the calibration table we already generated. One is delay and another one is the preliminary gain calibration. So it is also mentioned in the document. If you just follow that, you will get it. Where is band pass? Okay, this one. So you just need to do this thing. So first start with default band pass. Then you need to provide the name of the visibility and also the field name.
The important step, please do it rigorously.
Sorry. So I provided just the name of the visibility, name of the field. Then I also have these two table and I need to provide a new table name here, right? Sorry, it would be calibration table. And again, I am just copying this one. You can provide your own name, but just to be consistent with the document, I am just using the same name, okay? And note that they use this point B1 just to understand this is a band pass table. So B for band pass. So this is typically what people follow to remember what is going on. You can get all this information as Atharva mentioned in your logger file later on also. Okay, so I already mentioned the visibility, cal table, and field. Now the solid. Solid is infinite. So it is basically saying that you are solving for now F, right? Because you already taken out the time component in a separate table. So since you are solving for only frequency, you are solving for a single number for all time. So that's why infinite. Infinitive is not infinite, but it is basically taking the all time. You are just solving for a band pass for a particular antenna as a function of frequency. So that's why it is mentioned here this. And then you also need to mention the reference antenna every time, right? You have this reference antenna. Yeah. Like you cannot do multiple reference antenna for different calibration tables. So you need to have a good antenna and keep it same for all the tasks. And again, minimum SNR is 2.0. And you are solving for band pass, which is B here. And you also mentioned the gain table, which you generated before, right? You are providing the time component, which is one table, and also the delay component you generated, which is basically do the on the fly. Like when they solve for the band pass, they will take the information stored in that particular table and solve for your band pass. It is not applying to the data. It is just while generating the solution. So you already have generated two tables, right? So one is this K1. It should have, you should have this table in your path. And then you have this gain which you generated just right now. Sorry. So you provided these two tables which will be applied on the fly. It is also written here, like gain calibration tables to apply on the fly. It will not apply into the data. It will just take, while generating the calibration, they will also take the information stored in K1 and G0. Here again, you are basically normalize the solution. Since it is not gain, it is band pass, you are basically normalize the solution. And that's it. So you do INP, you will find what are the things you measure. So you have the visibility file, you have the band pass calibration table you mentioned. You are calibrating against 3C147. You are solving for frequency, that's why you're solving this infinite. So it's basically taking one solution for the entire time because you are just solving for gain as a function of frequency. You do not have the time here. Then you keep the reference antenna same, minimum SNR 2.0, solution norm, you are not doing the complex gain, so that's why you are normalized by the average solution here to 1. Then you mention the two table which you generated on the fly, which will take care of the delay component and also the preliminary, the time component of your gain. So I hope like you should have this thing correct, otherwise there will be maybe some issues later on. So are you guys at this stage, like in the bandpass stage? Just check. So the idea is for the complex gain, when you are basically applying this G term, then you do not normalize. But for the phase and bandpass, you normalize to 1. That is fine. This is like, if this is 1, then everything will go to 1. You are basically changing the true gain and correct for that while applying to the data. That's why in the complex gain, you do not apply the normalization, but for other cases you apply. What will happen? I think I have not tried what will happen. So if they do not apply the normalization in the bandpass and delay, I think, I don't know. Yeah, it will be absorbed in the gain. Probably they do not understand.
It will be applied when it's transferred down. Right? Like calculate the solution, then you transfer down to your caliphase and then target. At that point, it will basically scaled up in amplitude section.
So basically what he is mentioning that it is all are multiplicative, right? So when you finally have all the tables applied to the data, it will absorb at some stage because this is multiplicative with this term, right?
It's a scaling thing.
It is a scaling thing.
At some point, it will be scaled up to match with the original. When that scaling happens, it will be again relative. So it will be basically the multiplicative term will get absorbed in the calculation.
Because this is actually a scaling thing. So if you have one scaling thing here, all are multiplicative, right? These two. So it will be absorbed in that sense.
At some point, the scaling is just.
Okay, let's do the then bandpass calibration. I hope I have everything right. Okay. Oh. Oh, I have this extra comma here. Sorry. If you have it, you just run it. I will generate this table once again. Actually, I provide the name wrong. No, the issue is there is a inverted comma here, right? This one. I need to. लेटेक्स comma आ गया है.
हाँ आप अगर मतलब वो लेटेक्स से कॉपी पेस्ट कर दोगे
तो कैसे होगा? On this one.
कॉपी फ्रॉम लेटेक्स डायरेक्टली विथ द कॉमा हाँ go back. Okay.
Okay, so you can again look into the. Yeah, there are a lot of information, but there is not necessary to read all these things here. Yeah. So you can clearly see that this is close to 1. So yeah, if someone wants to plot the bandpass, you can do it like this. You plot it as a function of frequency and how the bandpass looks like. So typically GMRT bandpass will look like this. So it will rise up, stay flat, and then it will go down. And you can clearly see that it is close to 1 when it is being flat. So it is basically showing that it is working. So that's the only thing. So you can open the plot MS, you can choose the data, the table, which is basically your B1. And then I am plotting only one correlation, which is R or RR polarization. And in the axis, I choose frequency, and in the y-axis, it is amplitude. Okay. So there is no need to do it right now. All the tables will be saved in your path, so you can do it later on. So we are now close to the final calibration, which is basically the last complex gain calibration, which is this one, the complex gain calibration. They have some questions. Then the last time, what do you expect? তুমি এখানেই প্লট করতে পারো। You choose B1 axis, এটা amplitude করে দাও, frequency করে দিতে পারো, যাই হোক। Are you guys able to do the bandpass? Are you able to do the bandpass? No. Your bandpass is done. Okay. Yeah, it's straightforward. দরকার নেই G0 ইনিশিয়াল G0 ঠিক আছে ও ক্যালকুলেট B1 টা জাস্ট চেঞ্জ হয়ে যাবে আর ইউ তোমাদের হয়ে গেছে ক্যানভাস তুমি প্লট করে দেখতে পারো না 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 তোমার সাথে চাইও না না তুমি বেসিক্যালি সলভ করছো কি BIF এখানে কোনো টাইম নেই it's better to generate a single solution for all the time, right? This is as a function of time, you get a single. So, the single noise ratio boost code. If you are using small solving, you have multiple solution for multiple time. But if you are actually solving for frequency, right? There is no need. There is no time, right? The time component is already done with the the G0, right? So you are saying that when solving for BIA, you take that K1 and G0. So they will solve for this while taking care of K1 and G0 also. They will take the information from this and on the fly they will apply and then they solve for a band pass as a function of frequency. Okay. So time component তুমি আগে করে দিও সেখানে তোমার 120 সেকেন্ড বা যাই হোক না কারণ ইন্টিগ্রেশন টাইম অনুযায়ী সলিউশন চাই আর এখানে তোমার চাই না কারণ ইউ আর সলভিং ফর অ্যাজ এ ফাংশন অফ ফ্রিকোয়েন্সি কিন্তু কন্ট্রোল সি তে ওরা কোথায় যাও আরে তোমাদের তো হয়ে যাবে আমাদের বাকি ইউ গাইস 12:30 বেজে গেছে নিরুপম দেখো পড়াতে হবে আর তো একটাই ক্যালিব্রেশন বাকি আছে জাস্ট ফাইনাল ক্যালিব্রেশন ফ্লাক্স স্কেল অ্যাপ্লাই ক্যাল না 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 এই এটা ছোট এটা একটুখানি শোন এটা হতে দাও না কি আছে ওইটা এটাই সমস্যা না তুমি এখন অনেকটা টাইম জুড়ে আবার প্রতিটা টাইম স্যাম্পলে এখন একটা ফ্রিকোয়েন্সি সলিউশন হয় আবার একটা টাইম আবার ইউ আর বেসিক্যালি ডুইং লট অফ স্টাফ ওভারডুইং Okay, let's move on to the next one, the last final calibration, which is the complex gain calibration, right? You are now solving for GI as a function of T. And this is a complex quantity, okay, amplitude and phase. So I written like this, but it is basically a complex quantity. So this is what is mentioned here, the final calibration you are doing as a complex quantity, solving it here. So now let's again do the default gain cal. So what have you done? You have done this thing and now you are solving for this thing, okay? The time component of your gain. Then you mention a calibration table here, which is, I'm keeping it same as they mentioned here. Then you also mention the field. So far you are only calibrating based on flux calibrator. Then you, since you are now solving for as a function of time, you are providing a solution interval, which is 120 seconds, 2 minutes. Then you also need to mention the reference antenna, which should be the same as you are using for all your previous tasks, which is C02. Okay. Minimum SNR is again 2.0. And you are solving for gain type G. So this small g or capital G, whatever. So you are solving for G, you are solving for amplitude and phase because it is a complex quantity. And then you need to mention the gain table also, right? Because this is the table you already generated. Like for every 2 minutes, you are solving for a gain. Not necessary, right? So basically, like K1 is reference to C02. Now, if you use so you corrected for one delay in the beginning, then you do a pre-calibration of as a function of time, you then get a bandpass solution. So you are having two tables, one is K1 and B1. So B1 and K1 is done. Now you are just solving for this term. And you are also interpolating, right, as a function of time. So what is the interpolation technique we are using, which is nearest and nearest flag. Okay. So I hope everyone use all the parameters mentioned in the document. And the interpolation technique is basically when you use all other gain tables, how you interpolate the solution as a function of time. So we are using this nearest interpolation. Also keeping in mind how the flag is there, right? So that's a nearest comma nearest flag. So finally check how it looks like. I think it should be fine. G1, 3C147, 122nd, C02. So if it is done, let's do the calibration. So I guess it is done based on 3C147, and now you are also doing for the phase calibrator, because note that your phase is close to your target and you need to correct from some time variation as a function of direction also, right? Coming from ionosphere and all those stuff. No, they will take care of the flag part, yeah. Like if you have a large chunk missing, your interpolation will be wrong, right? It is difficult to do a nearest interpolation, but if you provide that one, it will take care of that flag channel and do a proper interpolation. So if you have a very large chunk of data missing, it would be really hard to calibrate. Yeah. Yeah, but typically they will try to do a smooth interpolation. But if you have a very large chunk, maybe it would be difficult to even interpolate. So that's why he's mentioning you take a good chunk of data and do separately work on that. This is typically case for GMRT band 2. 3, 4, 5, I think you can work with. Yeah. We already done the phase calibration. Now we are phase calibration. Sorry, we have not done. Yeah. So last one is obviously you now change your field to phase, FILD, and the name of that is 0538440. And note that most of the parameters are same. Your gain table name is also same, but you are also appending true. So what is basically happening is that you have a table which is something like this. So the first term you have solution for 3C 147, and since you are appending in the same table, they will append for your phase calibrator. Okay, so we have a same table. It is like appending your solution just after 3C147. So that's why you can notice that this append option is true. Okay, in the previous one it is not true, but now you have the same table. In the first chunk you have solution for 3C147. In the next chunk you will have solution for your phase calibrator. Yeah. So I provided append equals to true. So you have the first chunk is basically 3C147. Next is basically corresponding to phase calibrator. And the rest of the parameters are same. So if you have that, then you just run go.
Yeah. So phase calibration everybody is doing.
So the last step is basically now you correct for the gain of your phase calibrator, but you need to also correct for the flux of the phase calibrator, right? Because right now your phase calibrator has flux, which is just a correlation of two antenna. It has no absolute flux level. So you say that I know the absolute flux level of your flux calibrator. You know the gain. You are basically transferring that to your phase calibrator. That is called flux gain. It is also mentioned here, right? So flux density of the phase calibrator will be set in the following step. This is called the flux scaling. Sorry, I should do default. So provide the visibility again. Then I will keep the calibration table name same as mentioned in the document. So I have this calibration table where I know the calibration of the 3C147. I'm using that calibration table. I am providing a new flux table, which is this flux scale. And reference is where you are transferring that calibration. So your reference is 3C147 because you know that flux and position very well. And you are transferring that to your phase calibrator. So reference is basically, as mentioned, 3C147. And you are transferring that to your phase calibrator, which is so that is all it's doing, right? You have this calibration table, you generated this, it has all the information of your calibration. You are generating a new calibration table from that, which is flux scale, and you are transferring the flux, or you are basically setting the true flux of your phase calibrator, where you are taking the reference from 3C147 and applying that to, or basically transferring that to your phase calibrator. So once it is done, then you can also check what is the flux of your phase calibrator. It is basically coming out to be 1.99 Jansky. So it's roughly close to 2 Jansky. Okay. So previously it has no absolute flux, but now you have a calibration You know what is the true flux of your flux calibrator. You are using that information and setting a flux of your phase calibrator, which is coming out to be around 2 Jansky. So the last step is basically transferring the gain, all the gains to the target. So let's see, you have. So yeah, let's try to finish up to the flux scale, and then I can do the, or all of you can do the apply calibration. তোমার কি আর হবে টাইম কালকে কোন seems like আরো প্রচুর করে দিয়েছে। So initially you do not, so you have 33147, right? So it has known flux as a function of frequency that we know also right? And we know the position also. And this is we set from set Jansky. But if you plot your phase calibrator, which is whatever 0, 5, this flux, like if you plot it, this flux is uncalibrated. You have some random number there, because this is coming out to be just a correlation of VI VJ star, right? And this has no absolute value. It has some value, but I don't know how much Jansky it is, right? So what we have done is we generate all the gain, right? And store it in this ap.g1 table. So I know what is the gain of that, of this along that direction. However, I also know what is the flux of this thing. So I know, given that gain, what is the correct flux would be here. I also know what is the gain of the phase. I am now transferring that solution to the phase so that I have an absolute value of the phase calibrator. So it's basically a ratio thing. So you know that for flux F of flux calibrator, what is the G? You don't know the phase, the flux of your phase. That is, you don't know. But you know what is the G of that. You are just basically getting this one, flux of phase, right? By you know this GP, you know this GF, which is all stored in this file. So you are basically have this F cal times G P divided by GF. This is all it is doing. So by this equation, you know what is the flux coming out to be. That is coming out to be 2 Jansky. If you plot it before, you will not get 2 Jansky. But if you now plot it after applying this calibration to the phase, this is all in the table. We have not applied that to the data. When we apply that to the data, you will see that your phase is coming out, the flux, the amplitude is coming out close to 2. But this table is coming just using this simple linear algebra. Okay, so you know this thing from your set Jansky. You know what is the calibration of your instrument from by calibrating. This information is stored here. You also know what is the calibration of GP. That is also stored here. So you know these 3 quantity, you are basically setting what it is. That's all it is. Yeah, if you can have a single calibrator, then it's fine.
We can directly apply that.
Yeah, you can directly apply that to the flux curve. But typically, like in all observation, we have a one flux calibrator and one phase calibrator, which is different. There is a reasons to do that, because this is 22 Jansky, right? Okay, so it will come in the image. So let's say you are basically imaging this region. Okay, you have many faint source. This is around, let's say, 0.5 Jansky. Now, if you have one calibrator which is also sitting here, this is 22 Jansky, and this is an off-axis. So you are observing this region, and this is like 10 degree or 5 degree away, and you do not have any other calibrator. What will happen is this will always dominate. You will never see this faint source. Then the solution would be you do a direction dependent calibration along this direction. You peel that source, then these faint sources will pop up. That would be like high dynamic range imaging. This is also a major problem in most of the radio interference. So we typically, what we do, we have a flux calibrator which is far away, here, let's say here, and we also observe a phase calibrator which is not that bright. Like phase calibrator is 2 Jansky, right? As I found, it is 2 Jansky. This is fine. Like 22 Jansky to 0.5 Jansky is really difficult. It's the dynamic range issue. It will always dominate your data. So if you like at low frequency, what happens there, we don't know, like for UR kind of sense, we don't have this kind of many calibrator. Then we have only one calibrator. But if your instrument is stable, so we will say that, okay, I will have all the calibration generated from this calibrator and apply this to here. This is far away. So you are not, so you are observing through this, right? The line of sight along this direction has very much different than this direction. So your ionospheric condition here is largely different from here. So you always have a phase calibrator here, not here, probably very close here. So we know that, okay, along this direction, what is the gain calibration? We just apply this to the target later on. We don't do this based on this. And that is one of the reasons to do, like, when you want to do a high dynamic range imaging. So 0.5 Jansky is very good. You are basically, people are trying to measure like 0.001 millijansky, something like that, right? Like LOFAR or GNRT or BRPR. They want to see low source population.
To get to like at least imaging. So after this application is done, we'll just split the target and run a T-clean round.
Yeah, T-clean, you need to then mention like all the parameters, right? Image size. No, you mentioning is you need to explain all those things.
Or that they can figure out. Technically. Like ideally, the CASA document is online. It's available. Because we have time.
Flux scale is done, is now apply cal. Okay, so I am assuming that everyone is done with the flux cal, or basically flux scaling. Sorry, not flux cal. And now we are going to apply that calibration to your field. So far we just generated the calibration table. We have not transferred that calibration table to the data. So far what we have done, we have generated all these things. So these things are also this one. So now we are trying to apply this table to your measured data so that we can get back this one. Okay. So that is what mentioned here. So you are basically transferring your calibration to your different field. Okay, so we are now at the stage of applying the calibration. So we basically again put your visibility file here. You are first applying your calibration to your flux calibrator, which is 3C147. You mention the table which is now flux scale because you have the final calibration which is flux scale table. You also mention the delay one and you also mention the band pass one. Okay. And then in the gain field, you mention 3C147. Note that you have two calibrators. So you are applying 3C147 to 3C147. You cannot apply this to another one. Okay. And then interpolation, you can do nearest flag also, whatever you want. And then cal weight equals to false. You do not want to apply the data weights in your calibration table. That is, you do not want to do that. So that's why cal weight is basically false. Okay. So this is how you apply the calibration. So you are first applying the calibration, which is stored in your flux scale and all other calibrator calibrator table. You apply 3C147 to 3C147. And then you do just go. And the next step is basically now apply the calibration to the phase calibrator. Okay. So you change field to, which is the next step mentioned in the document. So you now apply the phase calibrator. Like the calibration solution you generated for the phase calibrator, you apply that to the phase calibrator. So you are applying this particular calibration here to the phase calibrator. Note that don't do the mistake because you are now applying this one which you have appended in this particular calibration table, right? You did that append task. So you have two solutions. One is basically CC147. In the first step, you apply CC147 solution to the 3C147, which is your first task. You are applying the solution from 3C147 to CC147. Next is you are applying phase calibrator solution to the phase calibrator. So your gain field is now this one, which is phase calibrator. Your field is also phase calibrator. Okay. So you are basically saying that you are taking now this solution and applying to the phase calibrator. And the rest of the parameters are same. And finally, then you apply the calibration to the target. So as Nirupam mentioned, you have flux calibrator, phase calibrator, and target, but phase calibrator is pretty close to your target, right? You have phase here, and you have target here, and roughly its direction is close. So you are now transferring the phase calibrator solution to the target. Okay, so that's why you use always phase calibrator to apply the solution to the target. So that's why in the last step you mention the field which is your target field Abel 3C7, but you are taking the solution from this phase calibrator and apply that to the target. So just to be very careful that in the last step you are applying your solution which is taken from your phase calibrator. So all this table has a gain calibration of your phase calibrator, right? So all it is doing is you take the solution from phase calibrator and then you apply that gain to the target which is mentioned here. So just to be careful, you cannot mess up here at this particular stage. Otherwise, everything will be, wrong. Yeah, so basically it's done. Now you have applied all your calibration to different field. So you applied flux calibrator solution to the flux calibrator field, phase calibrator solution to phase calibrator field, and then apply the phase calibrator solution to a target field. That is what you do. And I hope you are able to come up to this point. If not, then I think we can help. You already made an image.
এটা করছে ফার্স্টেরটা 1%
কি এররটা দেখাচ্ছে? Field expression parse error. ও না না, এই কমাটা দিতে হবে, এটা প্রিন্ট, ওটা হচ্ছে বেসিক্যালি লেটেকে লেখার সময় ওটা টাইপ হবে। এখানে এটা কিছু থাকবে না, জাস্ট কমা থাকবে না। বেসিক্যালি তুমি বলছো যে তুমি এই নিয়ারেস্ট মানে ফার্স্ট ক্যালিব্রেশন টেবিল থেকে সলিউশনটা নিয়ে অ্যাপ্লাই করছো। জানি না। নো 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 নো, ওটা একটুখানি মানে লেটেকে টাইপ করতে করতে মিস্টেক হয়। বেসিক্যালি তুমি প্রথম বেসিক্যালি 33147 এই টেবিলটায় রয়েছে, তুমি সেটা সেখান থেকে নিচ্ছ 147 and rest will be just same.
Okay, you can check your
Okay.
calibrations
Take
basically. The thing is that
এই টেবিলটাতে দুটো সলিউশন আছে না, একটা
we have not applied any like rigorous flagging so far, right? We have just done like a rudimentary basic level flagging, and that leads to some weird artifacts in your final data. So if you see any like weird shapes in your plots for amplitude, phase, anything, just be aware that it's due to not like a rigorous flagging. We have done a basic flagging round and that's it. But that should be enough for this data. It's not like it's not going to give you that terrible results.
Okay, so everybody has done flux scale. Flux scale. Flux scale and apply cal. Okay, I'm not getting
তো
any.
এইটা এখানে হবে না, এটা একটা ওটা লেটেকে টাইপও আছে। This thing. To do this. Oh, sorry. This laptop keyboard is something different. So now it will work. Even you have to change here also. What is basically saying is that this table has two solutions, right? One is for CC147, also for phase calibrator. You are taking from this table CC147, uska jo solution hai, you are just taking that solution only and applying that to your this field. And the rest are basically, and yeah, you remove that thing, it should work. Are you able to? At what stage you are in? Oh, then it's great. You're already there. That's great. Are you also like, you can help him, right? Yeah. Okay. Are you guys able to apply the yellow? No, it will take some time here. You loading something. Imaging, you need one lecture because some parameters you need to choose for imaging, right? We thought that this lecture would be right now, but it is already one. So probably we will do imaging tomorrow. Or if you, I don't know, they will announce something. WS clean, yeah. But yeah, tomorrow we have the entire day. We'll try our best to at least show you some image. You can do it. It will basically, the issue of CASA T-clean is it will, it is slow, fast. WS clean is very fast, T-clean is slow. And the second thing is also WS clean has some, masking capability, right? It will, so in your image, there will be a lot of junks, like bright points, so they have some artifacts around that. T-clean, so you can provide a masking threshold. You say that, okay, you do not clean those junks, and WS clean has a better option to do that. It's basically, so if you have a image of the radio sky, you have a target here, right? But you have a lot of other sources. But let's say you have a very bright point source here. What will happen if you make an image? There will be a lot of artifacts around this. So when you run in T-clean will also put a mask. They will put a mask here, but they will also take this thing. So this is wrong, right? You should not clean those things. WS clean has a better filter there or better masking capability. They will not clean those regions, but they will only take this region where the source is. So that is the advantage of WS clean. Yeah, so typical, this is you go to the central region. So let's say you have a source at the face center, you go to a little bit off and you draw a box here in the CASA T-clean, and around that region you estimate the RMS. That will be already mentioned in the within the CASA viewer. We will show that. We'll show that.
I think
The plot. Okay. Okay, I hope everyone done the calibration and applying the calibration. Now last step is basically plot MS to check everything is okay or not.
okay, so we have generated the gain table and bandpass table and applied the solution to the data. So now in principle, the data should look like, after all the calibration, data should make sense. It should not go like a haywire, right? So that's what Arnav is doing now. So after the calibration, now how we should see that how the calibrated data looks like.
Okay, so first I'm plotting time versus amplitude. Where is time? Time and then amplitude. You can see that you now need to change the column. So you apply that calibration, you have another column in your measurement table, which is corrected column. Okay.
Yeah, so the corrected column actually holds the calibrated data, not the normal data column. Data column actually is not tampered.
Yeah. And we also do this colorization for based on field. You can do it, you cannot, whatever you want. Here I am plotting as a function of time. So I am just plotting a single channel, let's say.
Yes, 120.
And okay, let's plot this thing. Try to see what. So now you can see that your flux is at that level. You have the phase calibrator, which is roughly 2 or something Jansky, and you have this target as you expect. So initially it was like huge scatter, and it was not at that level where you expect, right? Since your calibration is now working well, you get decent or whatever you expect, like similar kind of flux.
See, note that this plot has actually all the antennas, all the baselines.
Yeah.
Okay. Earlier, you remember all different baselines was going like here and there because they had different gains.
Right.
Now all the gains have been corrected for. Then as a function of time, we also have applied the gain. And now it looks
Huh?
all same. You see, all these data points have all the
Time
baselines,
UV
all
wave.
435 baselines
Huh?
as a function of time for channel
UV wave.
128.
There are still some artifacts left in the data due to like not rigorous flagging. But for this data, like it's enough to kind of give you a rudimentary image, which is what you will produce when you run tclean. But we have also provided you like a better flagged and better calibrated target file. Now, after this, you will split actually the target data from this general MS into a separate file. But we have given you a better version of that also, which is your target.tar. So if you have untarred it, there would be a better thing. But for now, just follow this same tutorial up to tclean at least. Like after tclean, you can get a bad kind of image with all the artifacts involved. And then you will see what like better flagging and calibration methods can do for you.
Okay, so yeah, now you can plot in various way. And another plot I am doing is UV wave, right? As a function of UV wave, let's first plot the amplitude. And right now, let's plot the field 0, which is your flux calibrator. Remove the spectral window and let's do some averaging also so that the RAM requirement would be less, right? So again, there are some scatter, it is also expected, probably some baseline or something is bad, but I can change this thing to, let's say, 20 to 24, or let's say a little bit larger. So you are getting something like that. So it's mostly fine, but there
Yeah.
are obviously some scatter here. I don't know.
Yeah. Yeah, I mean, some bad data is still there, but it's okay. I mean,
Yeah.
most of the thing is fine in a sense.
And you can also try to plot the phase. Yeah, okay. Oh, sorry, I am plotting phase. So this is also is a very nice way to see. You basically see a point source after calibration whose flux is around 22 to 24 Jansky and it is kind of flat. And that is what you are getting here. Okay.
Yeah.
And here I'm just plotting a single channel. So there can be some baseline is still bad, some channel is still bad, or some time chunk is bad. But overall, like you still get a very decent calibrated data here. And let's try to plot the phase. There it is.
By the way, you are plotting the corrected column here, not the data column.
Yeah, you can clearly see that the phase is also very nice. It should be around 0. So initially someone asked that your phase is like all scrambled and large phase gradient, but after your proper calibration, you get a very nice, I don't know, roughly within plus minus 10 degree.
Plus minus 5.
Yeah. It's about plus minus 10 degree.
Yeah. And it can be improved over self calibration also, but in the starting, it is very decent result you are getting. And there is another last plot I wanted to show is basically you're plotting the target. Now plot the target as a function of UV wave and the amplitude. Yeah. let's do an average probably to some extent. Yeah, this is also fine because you have a diffuse source in your field. So at low baseline, you would get large flux here, and at high baseline, you have contribution to the coming from only the point sources. So this is again showing the Fourier theory actually works. So if you have a diffuse source, it will be in the sky, large angle. In the baseline, it would be dominated in the low baseline region. So that's why at the low baseline, you have large flux, but at high baseline, it is mainly dominated by point sources. And when you actually make the image, you will get that there is a diffuse cluster at the center of your field of view. So yeah, I think these are like typical plots what one can plot to see whether the calibration is more or less fine or not. And you can play around with all of this. And next class, we'll try to make an image. Okay, so this is it for now. Key plot ko chalo. What are you trying to plot? Okay. So for the phase, I choose the field 0. Okay. A single spectral window, maybe not averaging over time. In the axis, I am plotting UV wave and as a function of phase. Okay. And then I do this range, putting it like, let's say, minus 100 to plus 100. Sorry. And plot it. Okay. So in an ideal scenario, it should be like close to 0, but you have some scatter within plus minus 10 degrees that can be improved over self-calibration.
Okay, so we have come up to this point, and it's good that we are doing it properly, and it takes time. Okay, so what I'm proposing is that today from 5 to 7, is it okay if we continue this session? Raise your hand if you have objection. You have objection? 7 बजे भी शटल है. IISc से RRI कितना दूर है? Come on. और कुछ है क्या? शटल छोड़ के और कुछ प्रॉब्लम है? हाँ ठीक है, शटल IISc से पकड़ लेना ऑटो. IISc का शटल 7:15 पे है. हाँ? They will come only for you. So yeah, you can ask them to come a little bit later also, right? Huh?
Yeah. So see, the idea is that we have reached a point where you have learned calibration, right? Then the entire discussion about imaging, we have not even started yet. Okay. So, and whatever time today afternoon, we don't have any more either lecture or a hands-on on this. There are one online lecture and then there is another lecture. So 2 hours afternoon. The only way we can reach up to some imaging and a little bit of, concluding properly is if we have maybe 1 to 2 hours of extra time, and that we can use today afternoon, evening, if most people are interested. Of course, if you feel like you want to go back, you can follow the file that has been provided. Try to do some finalize your calibration and do some imaging and so on. Then tomorrow you will be able to pick it up. So it's not that necessarily you have to be here. But if most people are interested, we can actually continue this session after 5 for 1.5 hours or 2 hours, like that. So then we don't know if we can do it. So once again, your last chance to say no. If you are not happy with it, please raise your hand. If most people are okay with it, then we have to ask for permission. We have to see if we can at all arrange it or not. We don't know that yet. But we'll check if we can do it, and then we will, if we can, then we will have that extra session.
So take it.
Okay, fine then. Yeah, so we stop here now and come back after lunch.